An intro to this chapter. The first thing I want to tell you is that plenty of, I was going to use the word lazy, but lazy isn't the right word for the students that have trouble with quadratics, whatever that is. Lazy is not the right word. Unfortunately, the way we teach math through elementary school and high school leaves some people with a mistaken impression. The math is so easy. You don't really have to do any work. You just got to watch the lessons and everything's fine. Many of you in this class are probably like that. You're probably used to the idea, if I just watch the lesson, look at a little bit of the review before the test, I'm going to do great. That's not going to work anymore. I'm sorry that that was the impression you were left with. Yeah. I apologize. I'm sorry that math was taught that way, that you were left with that impression that you weren't challenged enough up till now. I can tell you, the grade 11 version of you, the people who are taking grade 11 U right now, yes? If you're this time next year, you'll come back and go, starting here, start being the best math person you can be of yourself, because there's just too many details to just zip through anymore. Okay? That sounds foreboding. It's not. The people who do the work have no problem with quadratics. The people who just keep up with the homework don't have much difficulty here. Now, that's the bad news. Here's the good news. I know something you don't know about this lesson. A lot of these words are going to seem new and strange, and we do 3 chapters of quadratics. So a lot of these words and phrases and definitions I'm going to use that will seem weird today, you'll get so used to them that you won't have to really worry about memorizing them anymore. So this is just your intro to that. So no panicking through this. Just highlight what you need to, get down what you need to. Intro over. Reasonably long lesson, so I got to keep it rolling, but a lot of the stuff, there's not much I can say about it, except just tell you what the words are. Okay. Determine the properties of quadratic relations. I mean, at this point, you can be like, I don't even know what a quadratic is. Well, that's my job, show you what a quadratic is. So let's talk about linear versus nonlinear. Often data shows a recognizable pattern that is not a straight line. Sometimes a curve of best fit will be better. So what we've been doing up till now, everything we've done up till now, had some kind of straight line. And in science, when you do these things, if something looks like a straight line, you'll treat it as a straight line. But you must know that can't be the only option. It must have been frustrating up till now. I give you permission to be frustrated up till now and go, everything we do in math is straight lines. What happens if it's not a straight line? If it curves or something like that? Well, that's what we're starting today. We had to make you good at straight lines first. In fact, it was more about the algebra, the x's and the y's and moving things around, and x-intercepts and y-intercepts and all that stuff. Now we can move forward. Sometimes a curve of best fit is more appropriate than a line of best fit. In such case, a smooth curve. So if you got this in science class, you might draw a straight line and go, whoa, that's not a straight line. You might draw a straight line and go, I don't know why that's happening today. My pen is doing something weird. It's doing it every time. Okay, I'll switch to the straight line tool. Straight line. In science class, if it's a straight line, you'll draw a line of best fit that's straight and go, there, it looks something like that. But moving forward, maybe what you want is actually a curve of best fit, and maybe that's the first time you've heard that word today is curve of best fit, where you go, no, it looks to me like the data is doing something like that. Yes? I think the end of my pen is messed up. Can I find in the pile my other pen? Well, I'll keep watching for it. It's around here somewhere. Oh, there it is. Right there on the ledge. Okay. So how will we know if something is linear or not linear? That is, does it represent a line or not a line? Well, if you have the graph, it's pretty obvious. You can look right at it. But if you have the table, you might not be able to tell. And so in grade 9, you found out if you did the first differences, if consecutive y values kept going up by the same amount, it was linear. New piece of information. If instead the second differences, which are the first differences of the first differences, if they're equal, it's going to be called a quadratic. That is, it's not changing by the same amount, but the amount it's changing is changing by the same amount. What are you talking about? Here, let me show you. It's actually simpler than what it sounds. Let me show you. Determine whether it's linear or quadratic. Linear would mean the table is changing by the same amount every time. How do you do it? Here's how you're supposed to do it. You look at these two values and go, how much did it change? Some people in grade 9 do them in their head. You go 14 to 8, how much did it change? I encourage you to actually do the subtraction. Go, how much did it change? It ended at 8. Started at 14, it changed by -6 because we really want that negative value. So if you did them just in your head last year, when we go to do second differences, that might cause you a problem. So then next one, 2 minus 8, -6. -4 minus 2, -6. -10 subtract -4 is also -6. When you go -10 subtract -4, it's like -10 plus 4, so I get -6. And that was last year's question. You found that they're all equal, then you went first difference is equal. The relationship is linear. Does this ring a bell? Trying to decide how much to over-explain this by. Does this ring a bell, doing these first differences? It's one of the core things of deciding if something's linear is does the table go up by the same amount every time? Okay, here's the new example. And if you didn't understand the sentences I used, that's okay, I'm going to do it right here. In the new example, you go, okay, find the first differences. 7 minus 4. Which is 3. 12 minus 7, which is 5. 19 minus 12, which is 7. And 28 minus 19, which is 9. Last year, you would have looked and gone, oh, the first differences are the same. Therefore, not linear. If I were to graph this, it wouldn't be going up by the same amount every time. Here's the new information, if you've drifted off to sleep. In grade 10 then, we go, okay, the first differences aren't equal, but I can do the second differences and find the differences of the differences. Yeah. I've got these numbers over here, 3, 5, 7, 9. I'm going to find out how much they're changing by. 2. They're going up by 2 every time. And he's going to, oh, he did it by inspection. I'm sure he did. He looked 3, 5, 7, 9. He said it's going up by 2 every time. I encourage you to actually do 5 minus 3 equals 2. 7 minus 5 equals 2. 9 minus 7 equals 2. Mr. Todd, do I have to write the minus every time? I'll say no. Yes, if they're just really obvious like this, it's okay just to write them like that. But when they get a little funny, then you should definitely write all the subtraction statements down to make sure you're doing it right. Here's the new information. That whole big sentence is on the previous page. If this happens, if the second differences are all equal, therefore, second difference is equal. The relationship is quadratic. You're like, I don't know what a quadratic is. I'm like, I know. I'm just giving you your first piece of information about quadratic. A quadratic relationship happens when the second differences are equal. There's more to tell you. Oh, there's way more to tell you. I think I got 5 lessons of just telling you about quadratics and the things about them. But here's the first thing. You can tell from a table of values you're dealing with a quadratic if the second differences are equal. There, that's all. Not too carried away, too far. We're getting to know quadratics. Are there any questions there? Do you need more time? Is it tough to read my little 2's there? 5 minus 3 is 2. 7 minus 5 is 2. 9 minus 7 is 2. Is it okay? Okay. More time? Now, what seems like a separate conversation, but it's not. It's coming back to the same stuff again. New word, degree of a polynomial. The degree of a one-variable polynomial is the highest exponent. Seems pretty straightforward. It's actually a very handy term we definitely use a lot in grade 11 and 12. Degree is just find the highest exponent. That'll be the degree of the function or of the relationship we're talking about. So any term of the expanded form of the polynomial, we need the expanded form. What does that mean? We'll talk about that in just a second. If the degree is 1, it's linear. Okay, that's one way to know. If the degree is 1, it's linear. We already knew that. That's y equals mx plus b. If you don't see any exponents, we knew that was linear. Those were lines. If the degree is greater than or equal to 2, then it's nonlinear. So if you see an exponent greater than 1, it's not linear. Better yet, here, new information about quadratics. if the degree is 2. If the exponents you see, the highest exponent you see is exactly 2, that's what we're going to study this chapter. Degree 2 functions. So learn a lot about quadratics right here. The degree of this function, the highest exponent I see on x, oh, it's tempting to say 0. But what exponent is on x? 1. This is called a degree 1 function. We called it linear. We called it y equals mx plus b. I'm giving you a new word for it. Like, I don't like when math people do this and give us new words to say the same things. The reason we need the new word is because now we're going to go higher with the exponents. That's the big thing that's going to change. So degree 1 is called linear. If I graph this, I'd get a straight line. If I made a table of values, I'd get the first differences were equal. And all I'm going to change this chapter is go, we can have x squared now. Not just x squared. And oh boy, does it open a can of worms. We'll be at this for 3 chapters. We'll be at it for a month or so, just learning about what to do with squared. Because this is chapter 1. How many lessons are in chapter 1? 6 lessons and a test. That's 8 periods. And then we do 2 more chapters of quadratics. Yeah, lots coming here. So this one is degree 2. That is, the highest exponent I see on x is 2. Well, it's the only exponent I see, but degree says highest exponent. And this is called quadratic. You're like, I still don't know what a quadratic is. I know. All you have, the only 2 pieces of information you have about quadratics is the table of values, the second differences will be equal, and if I have an equation, we'll see exponent 2 as the highest exponent. Oh, now we need somebody clever, because this is not what it seems. What degree is this thing? She says 2. She's right. Don't let me confuse you, okay? Stick to your guns, because I'm going to try and confuse you. You're like, I don't see an exponent 2 on there. There's 3x, and there's a 2x. They're all exponent 1s. Why are you saying it's degree 2? The distributive property, okay? The distributive property is going to come back to haunt us in a big way here. We are going to distribute like crazy here. The good news is this distribution looks a lot like the distribution you've seen before. The 3x gets multiplied by both of those, and when you multiply 3x by 2x, you get 6x squared. And you get 3x times 4 is 12x. And if your algebra is a bit rusty, that kind of algebra is a bit rusty, it's okay. We're going to beat it to death. For now, it's enough to go, oh, I wouldn't have seen that. Geez. Okay, I see what you're saying. That when expanded, I'm sure that set it up here. We're going to go back. In expanded form, this is now a degree 2. This will also be a quadratic. What does that mean? We don't really know yet what quadratic really means. We know that the table of values will have second differences equal, and we know in expanded form we'll see exponent 2 as the highest exponent. That's all. That's all we got so far. What about this one? Threw this one in because I like this version of the equation of the line. He said, giving away the answer. Will you get exponent 2 when you expand this one? No. This one expands out to be a y equals mx plus b. And maybe you wouldn't need to expand it to know that. Or maybe you would. Maybe you'd expand it out. Okay? So this one is degree 1. And this is linear. What that means, if I graph it, I will get a straight line. If I do a table of values, the first differences will be equal. Trying to say those same things over and over again. So at this point in the lesson, we're like, yep, got all that so far. Do you have questions? On page 3 of 13, it's going to be close. Can I go? Yeah, for sure. More time there? Notice this didn't have a neither. It said linear, quadratic. Your homework might be neither. If you see a higher degree than 2, like a degree 3 or a degree 4, good. The bad news is we have to be able to say that's not linear or quadratic. The good news is we won't have to do anything with it in this course. We'll only do degree 2s. We got enough work to do on degree 2s. We won't worry about degree 3s, degree 4s. So here's a review of what I said so far. Linear, yeah. Somebody just showed up now. Read this chart. They wouldn't have missed any information. They might have missed some understanding, but they wouldn't have missed any information. It's all right here. Linear relationships. You do a line of best fit. There'd be a constant rate of change. The polynomials have degree 1, and the first differences are constant. Non-linear relationships, you often use a curve of best fit. Variable rate of change. Polynomials will be higher than degree 1, and they'll have variable first differences. The first differences will change all the time. Specifically, this is the box we want. This is what we're studying this chapter. And here's what we have so far. If you do a quadratic relationship, you'd need a curve of best fit. It's not linear. The polynomials will be degree 2, and the second differences will be constant. Okay? That's what we have so far. Questions? Given two relations graphed before, which one's the quadratic? Oh, that is hard. That is difficult. How are we going to know which one's quadratic? What weapon we only have one weapon. Oh, she's going right for the curve. She says, I see a curve. This could be quadratic. This looks linear on both sides. One linear over here, one linear over there. Well, it's not. Okay, can we agree? That's not quadratic. So let's go over here and make sure this one's quadratic. What's the only weapon we have to check if something's quadratic? The second differences. So we could go over here and make a little table of values for the points that are given. Let's grab some points that we have here. There's a point. 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 Totally going to give something away here. Quadratics are very symmetrical like this. They're the same on the left as they are on the right. That's not really in this part of the lesson, but I just give that away right now. So I have x value 0, a negative 1. I have x value 1, which is 6. I have x value 4. Oh, no, I missed some. I missed all sorts of points. What the heck am I doing? 2, which was 11. 3, which is 14. 4, which is 15. 5, which is 14. 6, which is 11 again. 7, which is 6. And 8 is negative 1. And if I do the first differences, I should not be surprised to find out they're not equal. So 6 minus negative 1 is 7. 11 minus 6 is 5. 14 minus 11 is 3. 15 minus 14 is 1. Negative 1, negative 3, negative 5, negative 7. Do we agree? Those are not equal. We're not surprised. The graph was not a straight line. The first differences weren't equal. But look what happens here. What's 5 minus 7? 5 minus 7. Negative 2. The negatives are going to matter here, so be careful. 3 minus 5. Yes, 3 minus 5. It is, that's right, it's right. Negative 2, good. But the negatives are going to matter here. You got to take the bottom and subtract the one above it. 1 subtract 3, negative 2. Negative 1 subtract 1, negative 2. Negative 3 subtract negative 1, negative 2. Negative 2, negative 2. We suspected that that one must be the quadratic, and we used second differences to make sure. Yay! Quadratic. Now, here's a word you might have actually heard before. The shape of this quadratic. All quadratics sort of look the same. They have this curving shape to them, and the shape is called, has anyone heard this name before? Do you know? It's a parabola. Over the next few weeks, you're going to get to know parabolas very well. That's what we're going to be working on. We spent all of grade 9 and the first part of grade 10 working on lines. Now we're going to work on parabolas for a little while. A. P-A-R-A-B-O-L-A. Yeah, that's good. Okay, what do we got so far? A quadratic will have second differences equal. It will have degree 2. And it'll make a parabola if we graph it. And that's what a parabola looks like. Let me give out something else away. When you throw a ball through the air, It follows a parabola. Not sort of, not kind of, exactly. That's why parabolas are studied so carefully, is because we see them every day. You'll see some bridges and arches shaped like parabolas on purpose because they have very strong properties. Okay? All of that coming up. But do you have questions about this so far? All of that? How am I going to tell if a graph's a parabola? Second differences. And then now that we see that shape, that curving ball through the air type shape, we have a name for it called parabola. Lots of stuff here. So if your brain's already hurting, then this is a good lesson. Yes? Reminds me of a good workout, you know? About halfway through, you're like, oh, this is starting to hurt a little bit. Yeah. Lots of words here. But here's the good news. We're going to use these words so much over the next 3 weeks, 4 weeks. You're going to get so used to them. It won't seem as weird as it seems today. So, a quadratic relation has the equation y equals ax squared plus bx plus c. Why a, b, c? What do we mean by this? Here's a bunch of examples. Here's some quadratics we'll study. We'll study like y equals maybe 2x squared plus 5x minus 1. Or maybe we'll study 7x squared plus 14x minus 8. Or maybe we'll put a negative out there. Ooh, negative 2x squared minus 4x plus 9. All sorts of different numbers we could use. Notice this says a can't equal 0, and there's a reason for that. If I make a quadratic with a 0 out there, I don't have a quadratic. I've got a line. That's not a quadratic. The a can't be 0. The b and the c could be 0. We can make a quadratic like, say, y equals 2x squared. That's a quadratic. So, an equation with x squareds in it. That's what we're looking for. And no x cubes, no x to the power 4, no higher exponents than that. We'll study those. The grade 11s are doing them right now. In the afternoon, I go and teach, and we're talking about degree 3s and degree 4s and all that kind of stuff. We'll get there. But for now, degree 2. Why should we mention a can't equal 0? If a equals 0, we get y equals bx plus c, a line. Now, there might have been a moment of wisdom that came in all that, where you're like, oh, the m and the b were just placeholders. That was just like training wheels on all this, the m and the b. It actually doesn't matter what letters you put out there, the a's, the b's, the c's. And you'll see with quadratics, a will be the first one, b will be the second one, and c will be the third one. Yeah? A will be what's on x squared, b will be what's on x, and c will be the number that's by itself. But more of that coming up later. Hopefully, just a little bit shaking your world about m and b and going, oh, we didn't have to call them m and b. We just did that because we were learning about them, and we wanted to all have the same letter to represent what's going on. So lots of scariness here. And I'm halfway through. Well, maybe I will make it. Mrs. Todd said her video was about 40 minutes long, and I'm usually about twice as long-winded as her. So I was worried about the time. Yeah. Her videos are nice. She keeps it short. She doesn't get all distracted like I do.
You go into more detail.
Yeah, and I don't. Sometimes that's good, and sometimes it's not. I understand that's a weakness sometimes. Sometimes I yammer on a little bit too long. Okay, let's get down to business then. This is where the lesson could have started. It could have started and said, I didn't even tell you about what quadratics. I don't tell you anything about it. I'd say, let's graph y equals x squared and see what it looks like. I've seen that taught that way before, where someone just walks up and says, well, what if there's a squared in there? What do we get? Well, we can study it. We build a table of values and go, what kind of things do we get when we graph y equals x squared? And all I'm going to do is take each x value, say negative 3, and I'm going to square it. What happens when you square negative 3, friends? Positive 9. So you don't have to write positive, but I'm going to write positive because I'm teaching this going, look, when you square negatives, you get positive. That's important in understanding the structure of parabolas. So then if I do negative 2 squared, I get positive 4. If I do negative 1 squared, I get positive 1. And if I do 0 squared, well, hopefully 0 squared is not a difficult one for you. But notice what happens, and I mentioned this earlier, when you do the other side of the parabola, you get the same numbers again. 2 squared is 4, and 3 squared is 9. That's kind of nice and handy when you're doing parabolas. If you've got one side of a parabola, the other side's going to look exactly the same. So let me graph that on here. My points were -3, +9, -2, +4, -1, +1, 0, 0, 1, 1, 2. Look how fast I'm going in the second half. Oh, stop for a minute, Mr. Todd, and tell them about that. Once I get to the second half, I'm just doing the matching points on the other side because this parabola, all parabolas are very symmetrical. The left side looks just like the right side. Now, notice it's not straight lines, it's curving. Oh, and hopefully you did better than me. My pen on the screen here is jumping all over the place. Mr. Todd, I thought you said they're going to look like a ball throwing through the air. They can. This one's upside down. So we'll look at downward parabolas, and this one's an upward parabola. What makes them upward versus downward? Oh, we're going to talk about that too. Yeah. Complete the table values below, plot the points, and draw a smooth curve. Did it. A parabola. So I could teach that like this and say, look at when you have a degree 2 and you graph it, you get this curving shape, very symmetrical, called a parabola, not a parabola. When people are first learning about this, they sometimes say parabola. Because it looks like it should be pronounced parabola, but it's parabola. You got to put the accent on the right syllable. Taught that way, it's like, okay, this isn't so bad. So I just sub the numbers in, and I get the shape of the parabola. Yes. But like y equals mx plus b, we're going to learn a bunch of shortcuts. Okay? Do you need more time on that parabola? Okay, let's do some more. Does it have some questions, or does it just give me another parabola to do? Oh, calculate the first differences. Okay, calculate the first differences. Go back to the parabola. See, this is like teaching it a whole nother way and going, well, now that we've made a degree 2 into a parabola, let's look at the first differences. -5, -3, -1, +1, +3, +5. Are the first differences in a degree 2 parabola the same? Are these numbers all the same? No. So the first differences are not the same. But take a look at them, though. Something's going on there. Let's specifically look at, I'll get my highlighter out. Let's specifically look at those. 1, 3, 5. Interesting. Is the next one 7? Is it? Could it be? Could it be that simple? I don't know if it's simple. Does the next one go up by 7? It does. Now we've got a graphing shortcut for parabolas. This parabola follows what we call the 1, 3, 5 pattern. You start in the middle, and then you go up 1, then you go up 3, then you go up 5. If you need another point, you go up 7. It might be easier than lines in some ways. Lines was always over 3, up 2, over 3, up 2. This one's over 1, and then you follow the 1, 3, 5 pattern. Interesting. Interesting new feature of parabolas. Show the step pattern on the graph. Oh, I did. Did I show it on the graph? There's my step pattern right there. 1, 3, 5. Is it good? And when you write 1, 3, 5, you write it with 1, 3, 5, and then dot, 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 because it keeps going. 1, 3, 5, 7, 9. It does that all the way through. Giant lie coming here. I'm going to tell you a lie. All parabolas follow the 1, 3, 5 pattern. I'll have to adjust that a little bit. To all patterns follow a 1, 3, 5 pattern. It could be we might have to double the 1, 3, 5 pattern or triple it. But we'll talk about that as we go along. Okay? I just want to mention that. So for now, I do want to say 1, 3, 5 is the basis of everything we're going to do. Does the graph have a maximum or minimum value? Ooh, what does max or min mean? Max is a highest point? No, it doesn't have a highest point. We could draw this forever, but it does have a minimum point. It has a minimum value. It has a minimum. What is the optimal value? What is the lowest value of the graph? 0. And I'm going to add another piece to it. I'm just going to say y equals 0. When we talk about optimal values, we're always talking about the y value. Okay? That's the first time I mentioned that, but I'm going to have to mention that a bunch more times, that we're looking for the lowest or highest value, and here the optimal value is y equals 0. You got questions? Maybe you don't have questions. Maybe you're like, okay, this is just all info. I got to learn. That's fine. Ooh. What if I put a negative out front? What happens then? Yeah, it just changes the y value. Okay? But I'm going to write it out here. Negative 3 squared, which is now negative 9. Negative 2 squared, which is now negative 4. Negative 1 squared, which is negative 1. Negative 0 squared, well, that's still 0. And negative 1 squared is negative 1. Negative 2 squared, which is negative 4. And negative 3 squared, which is negative 9. Now, that could mess some people up. I understand if it does. You're like, wait a minute. I thought when you squared a negative, or when you squared a number, you always got positive. What's happening here? I did get positive. Negative 3 squared is positive. But then there was a negative out front of the whole thing. So those positive numbers all became negative, and I get this graph instead. Which either makes perfect sense or is really scary. For some people, that's going to make perfect sense. I put a negative out front. It means all the y values become negative. It's just pointing downwards instead of upwards. So it's the exact same parabola, but pointing downwards instead of upwards. Is that surprising that that happened when they put a negative out front? You got some dances now. Is there a St. John's dance coming up? No, there's not. Is there? You got some dance moves now. You got y equals x squared. You got y equals negative x squared. You can just be up there going, doo, 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 doo. There'll be somebody, if you go and do that dance move, there'll be somebody in the room that goes, I got you. I know what you're doing. Yeah? Upward parabola, downward parabola. Now, just so you know, the grade 11s will have a little more advanced stuff. You won't have this year, but some of the grade 11s will be like, they'll have this going. Yeah? You can't do that. You'll be watching going, what are they doing? It's this or this. I don't know what you're doing. Maybe you could do this, though, from last chapter. Yeah? Y equals mx plus b? Some of you are unhappy with this whole situation. You're doing something with slope 0. You're like, I'm not doing any of this stuff. Just so you know. I don't know what it asks. What does it ask? It says, show the step pattern. Show the step pattern. The step pattern is still there. Do you see it? Down 1. Down 3. Down 5. This is what I was talking about with my lie. I said all parabolas follow a 1, 3, 5 pattern. This one happens to be a negative 1, negative 3, negative 5 pattern. Okay? So, is it a lie? No, maybe it was just missing some details. Yeah? I showed that on my graph. I did what it said. What did it say? Say, show the step pattern. Did it. Negative 1, negative 3, negative 5. So I just need to change my sentence. All parabolas follow a 1, 3, 5 pattern. Still more to the story coming. This is just lesson 1. Does the graph have a maximum or a minimum? Maximum. Mr. Todd, your son's name is Max. Did you name him after parabolas? Well, I hope not. I don't remember thinking that, but maybe it was in the back of my mind somewhere. My other kids' names are calculus, geometry, and Pythagoras. So I don't think there's a pattern there. I should have named them 1, 3, and 5. Maximum. Do your parents, when they're mad at you, use all your names? Like when Mrs. Todd's mad at my son, she'll say, Bennett, David, Joseph, and he's like, he knows when she uses all the names, she's in trouble. That's what I call my son when I'm mad at him. Maximum. I don't know why maximum. I should say Maximus. That would be cool. I go maximum, and he's like, what is the max value? 0? Yeah? It's the highest. Where is it? Highest. What's 0 there, though? I know both the x and the y are 0 there, but when we talk about optimum value, we'll be talking about the y value. Imagine this was a ball flying through the air. Its highest y value is 0. We'll be talking about the y value. More on that later, but I just mentioned for optimal values, we want that y value. How can the highest be 0? Well, maybe I'm standing on the edge of the cliff, and the cliff is 0 to me, so the ball came up to, I don't know. More on that later. Good stuff coming. And those of you who want to take physics next year, lots of this coming up. I did all that? I did all that? A review of everything we've seen so far. The graph is symmetrical about the y-axis. It's the same on the left of the y-axis as it is on the right of the y-axis. We call the y-axis the axis of symmetry. Wow. You want your parents to leave you alone tonight? Just drop that phrase on them. Come on and say, oh, I was hoping you could empty the dishwasher. You're like, I'd like to, but I got this homework. We're doing axis of symmetry. It's really difficult to be like, okay, forget it then. That's a good phrase, axis of symmetry. Looks really difficult, but in the end, it's just the center line. That's all. And it has the equation. Oh, now we need someone really clever. Let me draw the axis of symmetry on this baby. Where is it? Back here. Axis of symmetry coming at you in another color, giving you lots of time to think out, because this is a tough equation. That line right there, oh, we haven't done it in weeks. What is the equation of a vertical line? Y equals 0 was this one. So this one's x equals 0. Good, right on top of it, the two of them together. Hey, take it easy. Oh, testing the microphone, testing the microphone. There we go. Maybe, uh-oh.
I didn't think it would like embrace.
So you forgot what color rice was. So now you have a lot of rice.
You'll have a sausage tonight. Make good food and good something. Right, Mr. Todd?
What?
Exactly.
Yeah, exactly.
But it's thoughtful.
Well, I don't know. It booted me out, but then it recovered my file. Maybe it's okay, I don't know. We'll see how the video survives. The axis of symmetry has the equation x equals 0. It's totally fine if that freaks you out a little bit, if you don't remember that too much. The point where the parabola intersects the axis of symmetry. What? The parabola intersects the axis of symmetry at that point right there. Has anyone seen the name of this point before? It is the origin in this particular case, but on a parabola we call it the vertex. Yeah, it is the corner of shapes where two sides meet. And here it's where two lines meet, where the parabola meets the axis. The vertex is the extreme point of the graph. That's the word we're going to use, and we're going to use that word again and again, the vertex. there's a pattern in the differences. Starting at the vertex. Each time you move right or left one, you're increasing by the odd numbers. There's the 1, 3, 5. Did you just hear a beep? This lesson, the things that rebooted. Somebody gave me food that I ate before I started. Some alarm going off. We'll be lucky to land this lesson. We call this pattern the 1, 3, 5, ... pattern. Or we call it the step pattern. Very helpful when graphing, the step pattern. Okay, Mr. Todd. Pretty boring lesson. Y equals x squared upwards. Y equals negative x squared downwards. Please tell me we're not leaving without something with a little spice to it. Yeah, here it comes. Need more time here? Spicy example to finish up with. Here's what we want to accomplish over the next month or so. We want to be able to handle something like this. Y equals 2x squared minus 4x minus 6. Really scary. Okay? So we're going to do a really scary example to finish up. Okay? They gave us the graph though. So I took Desmos or something like that and graphed it to say, what can these parabolas look like? They might move around on us. Why is it moving around like that? We don't know. We don't know what's happening, but it's a parabola. Is the first a value positive or negative? Right there. Is this positive or negative? Positive. Does the curve open up or does it open down? Up. We call this up. I can see someone thinking that the vertex is pointing downwards, it's downward. But we're talking about which way does it open. So it's opening up, yes. That actually, those two things are connected. There's a big spicy moment with parabolas. If the number in front of x squared is positive, we're going to open upwards, negative downwards. And so now you've got some lyrics for your dance. Yes? You can yell it out to everybody on the dance floor. Positive, negative, positive, negative. You're going to be walking across because your parabolas can move now. You're ready for the dance now. If the first term was negative, what do you think you're going to get? Downwards. Shh. I'm almost done. I know it's not the most exciting lesson ever. Stick with me for the last couple. Indicate the y-intercept in the graph. Here it is. One y-intercept. What is it? Negative 6. Oh. Negative 6. Is it that simple? Yes, it is. If we're in standard form, which is y equals ax squared plus bx plus c, c is the y-intercept. So maybe we know or could know a little more on this spicy example than we think. There's still lots to know. Why did it move over here? Why is it so far down? You know, there's lots to talk about, but at least we can get the y-intercept. So far we know the sign of the a value tells us how the parabola opens. The c value is the y-intercept. And verify with the graph shown. Well, I can see that right in the graph. I did that before I got to that moment. Is it okay? Lots of spice coming in later lessons. This gets out of hand, let me tell you. Whole month of this. Anyways, I think it's just a review at the end, is it? Oh yeah. Y equals ax squared. If a is positive, it opens upwards, and the vertex will be at 0, 0. Y equals ax squared. If a is negative, it opens downwards. And then we have axis symmetry and those step patterns there. Is it okay? Sign work 136 to 137, 1, 2, 3, 4 ACE, 5 AC, 6, 7. Get to it. Parabolas is not going away, folks. We're doing lots and lots and lots and lots of parabolas.